Hello everyone, I'm going to take you through pharmaceutical chemistry, and majorly we have what we call pharmaceutical chemistry 2. Pharmaceutical chemistry 2 deals with the inorganic part of chemistry, where we look at the different drugs derived from inorganic chemistry. Since last semester we have already covered about organic chemistry, that is the study of carbon and its compounds. So this time we have to switch to something new, that is inorganic chemistry. So inorganic chemistry deals all about group elements of the periodic table, where we know that a periodic table is divided into two. We have periods and then we have groups. So it is also good to appreciate why specific elements belong to a specific group and why others belong to the other group. So today I'm going to take you through group 7 elements of the periodic table, or group 7 derived drugs of the periodic table. So this is our outline for today. We are going to look at introduction to halogens. We shall look at atomic structure of halogens. We are going to look at the physical and the chemical properties of halogens. We shall look at halogen compounds, where we are going to interact with majorly 3 compounds of halogen. That is, when halogen compounds combine with hydrogen, when halogen compounds have oxygen compound in it, or oxygen element in it, and then when we have our group 1 elements of the periodic table combining with halogens, where they form alkali metal halides. So group 1 elements are called alkali metal halides. So after we have looked at the different compounds, we are going to look at hydrochloric acid as one of the compound of this group, or halogen compounds, and then we also want to know the different properties of our hydrochloric acid, the uses of hydrochloric acid, and then here we come to another compound, where we look at chlorinated lime. We have others as alkali earth metals, where in alkali earth metals we want to look at the different sources of alkali metals, medical applications of alkali metals. And then after that we shall look at iodine. We have the different sources. We shall look at what are the different sources of iodine, what are methods of preparation of 5% and 10% iodine solution, and then identification test on salts of sodium chloride. And then we shall have identification test on HCl, or hydrogen chloride. So let us start straight away by looking at introduction to halogens. Halogens are group 7A elements, and this includes the following. We have fluorine, we have chlorine, we have bromine, iodine, and then the last is astatine. So you should know how to write the chemical symbol of fluorine, you should know how to write the chemical symbol of chlorine, you should know how to write the chemical symbol of bromine, you should know how to write the chemical symbol of iodine, and then you should also know how to write a chemical symbol of astatine. So the first 4 elements are encountered in nature, while astatine is prepared artificially and is very unstable radioactive element. So first 4 halogens, that is fluorine, chlorine, bromine, and iodine, we find that we can encounter them in nature. While astatine, we don't find it in nature. In case we need it, we have to prepare it. Why? Because it's very unstable, and the instability is brought by its radioactive property. So we cannot easily find it in nature or encounter it in nature. Halogens as well are univalent in most of their compounds. Univalent meaning they have one valence, or we can also call them monovalent, is the same as univalent, having one valency. So let us see how the atomic structure of halogen is. How does it look like? The outermost electron layer of halogen atom has 7 electrons. Every element of group 7 of the periodic table has 7 electrons in their outermost shell. However, they readily accept another electron to form a singly charged negative ion. Since it only has 1 electron left to become stable or to attain the charge of a noble gas, it has ability to gain. Gain is attract. We can say it has ability to attract another 1 electron. That is why here we have said accept, so we can say attract 1 other electron so that it becomes stable, and when it is now stable it gains the configuration of a noble gas. Okay, because we know noble gases have all the outermost energy level covered, and we expect every outermost energy level to have 8 electrons in them. So do a specific research on electronic configuration of halogen atoms. Like, you have to write them down in your free time. Write for fluorine, write for chlorine, write for bromine, write for iodine, as well as writing for astatine. So we have properties. We need to know the different properties of halogens. Here we have halogens exhibit properties of nonmetals or metalloids. Electronegativity decreases down the group, hence fluorine is more polar than astatine. Halogens are diatomic molecules, and then we see that all halogen atoms have a very pungent odor. All halogens are oxidizing agents, but the property decreases down the group. With fluorine, this should be an I. Make sure you correct that. It's supposed to be I, with fluorine being the strongest oxidizing. This Z should be I. Meaning, if fluorine is the most oxidizing or the strongest oxidizing agent, meaning other elements are weaker down the group. For example, chlorine is greater than bromine in oxidizing property, while fluorine is greater than chlorine in oxidizing property. Okay, so you need to have that at the back of your mind. However, we need to continue noting. We see that fluorine is the most electronegative and the strongest oxidizing agent, just like what we have said. Fluorine and bromine are very toxic and are not used in medicine. Element fluorine and bromine, we are not going to interact with it in the field of medicine, but we shall interact with chlorine and then iodine. So chlorine is used as an antiseptic for disinfecting water. The water we take, it is always chlorinated, as in they add the chlorine agent in it. Iodine is only halogen used in medicine in form of alcohol solution. So the 5% we talked about earlier on and the 10% are majorly alcohol solutions of iodine. And we are going to encounter how we can prepare them, what we need to know or what we need to have to prepare them. What is the method of preparation? All halogens can irritate the respiratory tract and cause inflammation. That's what you have to know. However, we want to see the different halogen compounds that we shall encounter or that we shall interact with. Here, as I said earlier on, they are classified. One, we have hydrogen halide. A hydrogen halide is a compound that contains hydrogen and halogen elements only, and includes hydrogen chloride. We can even start with hydrogen fluoride, but since it reacts explosively to form hydrogen fluoride, so that's why we are starting with hydrogen chloride. We have hydrogen bromide and then hydrogen iodide, and these are their chemical symbols. Here, this is for hydrogen chloride, hydrogen bromide, and hydrogen iodide respectively. Respectively is like in order, okay? And then we have oxygen compounds of halogens. Halogens form acids consisting of oxygen atoms. Halogen hydrogen atom is hypochlorous. These are the acids: hypochlorous acid, hypobromous acid, and hypoiodous acid. And then these salts of the salts of these acids, such as sodium hypochlorite, and this is sodium hypochlorite, and potassium hypochlorite, are pharmaceutical preparations, and the others that we looked at in class, by the way. So we are starting right away with the compounds that contains hydrogen and halogens only. Those are hydrogen halide compounds. Hydrogen halides are inorganic compounds that contain hydrogen atom and halogen atom. Hydrogen halides include hydrogen fluoride, hydrogen bromide, hydrogen chloride, and then we have hydrogen iodide respectively. So we can see their chemical symbols there. But our main interest for this, for the field of medicine, is majorly hydrochloric acid. So let us look at a few physical properties of hydrochloric acid. Hydrochloric acid is a clear, colorless liquid, soluble in water. It dissolves in water, soluble in water, has a excuse me. Soluble in water, has a strong pungent odor, and then it's highly corrosive. The density varies with concentration. Chemical properties of HCl: dissociates completely in water, forming hydrogen ions and chloride ions. Then we have reacts readily with bases to form salts and water only. So here, when they say dissociates completely in water, forming hydrogen ions and chloride ions, so we see that since it dissolves in water, when in the process of dissolving in water, it is going to dissociate completely to form both a cation and anion. The cation that is going to be formed here is the hydrogen ion, and then the anion that is going to be formed is our chloride ions. We see that another chemical property is when our HCl reacts with the bases to form salts and water. We know that every acid reacts with a base to form salt and water. For example, we can have sodium chloride. So I'm not sodium chloride, but sodium hydroxide is a base. Sodium chloride is a salt. Okay, so we cannot use it for making or reacting with acid. So I'm going to say that, let me repeat myself. An acid reacts with a base to form salts and water only. And I was trying to give an example of sodium hydroxide reacting with our HCl, that is hydrochloric acid, or hydrogen chloride, another person can call it that way, to give us salts and water only. So concentrated HCl dissolves many metals to form oxidized metal chlorides and then hydrogen gas. Methods of preparation of HCl. HCl has briefly 3 methods of preparing it. One of the methods is what we call direct synthesis. Direct synthesis is when we use a mineral when we use a mineral called brine. Brine is a mineral that has a mixture of both sodium chloride and water. So our brine undergoes electrolysis, or we electrolyze it, producing chloride gas, sodium hydroxide, and then hydrogen gas. Pure chlorine gas can be combined with hydrogen to produce hydrogen chloride. And then we have equation of reaction, because we know that under electrolysis we have both the cathode and the anode. So you find that these two gases are produced from both an anode and then the cathode. So we should appreciate that at the cathode there is reduction type of reaction, and then at anode we expect oxidation to take place. So we find that our chlorine gas is formed at the anode, and then the hydrogen gas is formed at the cathode. The reducing hydrogen chloride gas, the resulting hydrogen chloride gas is absorbed in deionized water, resulting in chemical pure hydrochloric acid. What do we mean by deionized water? Deionized water is water that does not contain any ions in it, be it non-metal ions or metal ions. We don't need them in that water where we are going to absorb our hydrochloric acid. So we have the second procedure of preparing, that is organic synthesis. In the chemical reaction, hydrogen atoms on the hydrocarbon are replaced by chlorine atoms, where upon the released hydrogen atom recombines with a spare atom from the chlorine molecule, forming hydrogen chloride. And we have equation of reaction, that is, this is our organic compound reacting with chlorine. This is, for example, halogenation of alkanes, giving us an alkyl halide, HCl, and then we see that this alkyl halide further continues to react with a strong oxidizing agent, that is hydrogen fluoride, and it will give us alkyl halide and HCl. The resulting hydrogen chloride gas is absorbed in water, and then we shall have received or manufactured HCl. Another method of preparation of our hydrogen chloride or hydrochloric acid is when we use the laboratory method. So for us to use a laboratory method, we need a salt, and that salt should be sodium chloride salt. It should react with sulfuric acid to produce sodium hydrogen sulfate and hydrogen chloride. So here we have sodium chloride plus sulfuric acid. This is the chemical symbol of sulfuric acid. This is the chemical symbol of sodium chloride. So we form sodium hydrogen sulfate, and this is the structure, and HCl. This reaction proceeds, and it's heated at a temperature of 200 degrees centigrade. So when this continues, we expect to have this in solution and then more of sodium chloride. So that's why we have sodium chloride reacting with the sodium hydrogen sulfate to give us now our HCl. More of the HCl is going to be collected, and sodium sulfate. So those are the three methods of preparing HCl. We have the laboratory method, we have the organic method, and then we have brine, or the one that needs electrolysis, direct synthesis. They call it actually direct synthesis. Alright, so we have uses of HCl, uses of hydrochloric acid. But what we need to put in mind, we have two concentrations of hydrochloric acid. We have dilute hydrochloric acid, and also we have concentrated hydrochloric acid. However, dilute hydrochloric acid is preferred in medicine to concentrated hydrochloric acid. This hydrochloric acid is going to be administered orally in drops, meaning we are going to use the oral route of administration, or in the form of mixtures, most often together with pepsin, to improve gastric acidity. We all know that in the GIT, in the GIT we have the stomach, which is responsible for digesting proteins, and the enzyme present for digestion of proteins is pepsin. So In the stomach, we have acidic medium, and that acidic medium is as a result of our hydrochloric acid. So when there is when there is maybe indigestion of proteins, the proteins are not digested well, we find that we have to administer our patients or give our patients this dilute hydrochloric acid in drops, or in form of mixture. We mix it with pepsin so that we improve the gastric acidity in the stomach. Hydrochloric acid improves absorption of iron preparation, hence most often prescribed together. So since it improves iron preparation or absorption, we find that they can easily administer them together or in the form of mixture, so that it aids absorption of iron preparation. Iron preparation like ferrous sulfate. Ferrous sulfate is majorly used together with folic acid to aid in replication of red blood cells, more red blood cells in the body, and thus helps to prevent anemia. Used in production of vinyl and alkyl chlorides. And this takes us back to our organic chemistry, where we looked at this preparation of vinyl and alkyl chlorides, used in preparation of chlorides and then fertilizers and dyes. So how can we identify HCl? It takes us to identification test of HCl or hydrochloric acid. So in this specific compound, we first identify the ions that we have. When it completely dissociates in water, we have the hydrogen ion and then the chloride ion. So when we look at the hydrogen ion, which reagent can we use to identify? We find that we may not have a specific reagent we use to identify the presence of the hydrogen ion. However, when we look at the chloride ion, we see that these are halogens here, and we can easily identify them, or they have a specific reagent that we use for identifying them, and that reagent is our silver nitrate. So when silver nitrate is added to hydrochloric acid, we expect a white precipitate if a chloride is present. So that's why we are saying a white precipitate of silver chloride is observed. The white precipitate is soluble in ammonia solution, dissolving to form a colorless solution. So for us to confirm that the white precipitate that we have formed is silver chloride, we have to react it with ammonia solution. If it dissolves in ammonia solution, we shall make a conclusion that the chloride confirmed present, chloride ions was confirmed present. If it does not dissolve in ammonia solution, we are going to conclude that the chloride ions were absent in that specific solution. Okay, because you can be given solution X and then you are asked to identify which ions are in solution X. So we need to have that at the back of our mind. So we have silver nitrate plus HCl giving us silver chloride, and then nitric acid. Silver chloride reacts with this is the second equation representing the reaction with ammonia solution. Ammonia solution is written like this. This is the chemical formula for ammonia solution to give us this compound, a complex which is soluble in water. Okay, and then our water. So that is how we can identify HCl. However, we have what we call assay of HCl. Assay is a titration that we do for HCl or hydrochloric acid, that we have pharmaceutical assay. So what you need to know about pharmaceutical assay is a titration in simple term, another word for it. Or we can call it qualitative analysis. But this that we have just done identifying this is what we call quantitative analysis. So qualitative analysis, another word is titration, another word is pharmaceutical assay. So when we are looking at an acid, this is an acid. For us to carry out a titration is majorly to get to know the unknown. So when we have hydrochloric acid, we are going to look out for a base. And the most preferred base we are going to look at is sodium hydroxide. Yes, we need sodium hydroxide reacting with HCl, and then we also need what we call indicator. The indicator that we shall use is methyl orange indicator. So we expect to know how to write the equation of reaction of HCl and sodium hydroxide, and then you also need to know the indicator. But the name or the method of assay of sodium chloride, of hydrogen chloride and sodium hydroxide is what we call neutralization, because when an acid reacts with a base, that type of reaction that has happened is neutralization type of reaction. The acid or the base neutralizes the acid, forming a salt and water, where we saw that equation some time back in under chemical properties. That is why you are not able to see it here, but you need to put it at the back of your mind that that is the assay we have. All right, thank you. This marks the end of hydrogen halide compound. We want to look at a new compound, and that is chlorinated lime. All right, so we have chlorinated lime, or another name for it, we call it calcium hypochlorite. Chlorinated lime has a formula, and this is the formula, okay, of chlorinated lime. It is white or a grayish white powder. The substance is dissociated into calcium ions. This is our calcium ions, and then hypochlorite ions in water. So here we see that we want to see how these salts can be prepared. So this is production or preparation of calcium hypochlorite. It is produced industrially by treating lime. Lime is calcium hydroxide, or we can say chlorinated lime, lime water. You can say it's treated with lime water, or you can just say it's treated with lime, and that lime is calcium hydroxide. So we have calcium hydroxide with chlorine gas, and then here we see that we have formed our calcium hypochlorite, calcium chloride and water, and we see that this equation is well balanced. Okay, so after that we need to find out the uses of our chlorinated lime. Chlorinated lime or chlorinated water, you can say it is a bactericide, meaning it kills bacteria. It is a disinfectant, and then used as a bleaching agent. We can also use it for water treatment. It's actually what we add in water, and then we smell the chlorine stuff. Water treatment, and then oxidizing agent. So those are uses. That is all about chlorinated lime. Nothing much or exaggerated that has to be known about it. So let us go straight away to alkali metal halides. So alkali metal halides include sodium chloride, potassium chloride, sodium bromide, potassium bromide, sodium iodide. Are the most commonly used pharmacopoeia preparations. Pharmacopoeia preparations are like what we have that we always use as maybe active pharmaceutical ingredient. or maybe as other preservatives and the rest. Like, it is a known preparation, it exists and it is used for preparation of other compounds. All these inorganic compounds have a common feature, both in the ways they are produced and their properties. These different compounds above, you find that both of them are produced in a specific manner or in the similar method of preparation, as we are going to look at it down. However, the method of analysis of analyzing them are similar, but their action on organisms differ. Okay, that is what we have to note. Sodium chloride is the only alkali metal halide that can be found widely in nature as a massive deposit of rock salts. Please put that in mind. Excuse me. We have what we call preparation of alkali metal halides. We are going straight away to how we can prepare them. Preparation of sodium chloride and potassium chloride, the chlorides, can be sodium chloride or potassium chloride. A purer solution can be obtained by treating sodium carbonate. We are going to get carbonate, treating it with HCl or hydrochloric acid. So if we want sodium chloride, we get sodium carbonate. If we want potassium chloride, we shall pick potassium carbonate. So in this specific case, we want sodium chloride first. That is why we are picking sodium carbonate, reacting it with the HCl to give us sodium chloride, carbon dioxide. Of course, this is a small 2 when you write it in your books, and then water. Make sure that you put the states and always make sure that it is balanced. You find that sodium chloride is a solid, sodium carbonate is a solid, hydrogen chloride is aqueous, sodium chloride is aqueous. We have carbon dioxide gas and then water. However, this gas evolved, we can test for it or confirm what it is. And what chemical we use for confirming it is our lime water, that is calcium hydroxide. You find that it turns the calcium hydroxide milk. Okay, it turns calcium hydroxide milk. That confirms that it is carbon dioxide gas being evolved. Somebody can say it makes a turbid solution, it's the same as the milky. Others even see it as a white precipitate. So even but the most appropriate one is turbid and a milky solution. Some people actually call it a cloudy type of solution. So when we want pure potassium chloride, we still use the carbonate, as I said earlier on. We take potassium carbonate reacting with the hydrochloric acid to give us potassium chloride, carbon dioxide, and water. The byproducts of reactions are volatile. Therefore, the products are produced pure. The products that we get are going to be pure. So here we have preparation of sodium bromide, sodium iodide, potassium bromide, and potassium iodide. Bromides and iodides are produced in the industry as follows. Okay, so by now you should know how to prepare sodium chloride and sodium bromide. We are switching on to the bromides and iodides. So for them, they also have a similar way of preparation. That is why we are dealing with them together. So the first statement here says bromides and iodides are produced in the industry as follows. What you need to write down is the first step, that is iron shavings are treated with the water. Then bromine or iodine is added. So if we are going with the bromine, we go with the bromine first. We add bromine and then we add iodide. And then the product formed is iron bromide or iron iodide. That is, if we took the iodine, we form iron iodide. That is iron 2 iodide. And then iron 2 bromide. Those are the 5 things we form. So we react. If it is iron 2 bromide, we are going to react it with more of bromine. When we react it with more of bromine, we get what we call a ferroferric bromide. And then when we react it with the iodine, we are doing it hand in hand with the other, since they have the same procedure, to avoid you first writing for bromides and then writing for chlorides. I mean for iodides. That's why we are doing them one at a time. So we get this ferroferric iodide. The solution of ferroferric bromide or iodide is evaporated. Okay, so sodium carbonate solution is added, ferroferric solution is formed. I mean, to a ferroferric solution, it can be a ferroferric bromide or a ferroferric iodide. We are going to add sodium carbonate. If we want sodium bromide or sodium iodide, we add sodium carbonate. If we want potassium iodide or potassium bromide, we add potassium carbonate. So here we want a sodium compound, either iodide or bromide. We add sodium carbonate to it. The precipitate of iron hydroxide is filtered off. So when we react, we form this different precipitate, and we need to filter off iron hydroxide. It will be a precipitate, meaning in solution we shall remain with our sodium chloride, I mean bromide or sodium iodide. After evaporation, sodium bromide or iodide crystallizes out of the filtrate. So you crystallize it out of the filtrate. Like crystallizing can need you maybe to evaporate it, heat it, and then you get crystals. For example, if you put water, salts, common table salts in water and then boil it or put it under heat, you will find that at the end, when all the water has drained, you will have the salt particles remaining. Okay, so the same thing here. After we have filtered, we put it on heat, and then that's why we are saying evaporation. That is like exposing it to heat. After we expose it to heat, we shall now get the sodium bromide or sodium iodide. The same comes to potassium carbonate. We add it to the same procedure in order for us to make potassium bromide and potassium iodide. So we have medical applications of sodium chloride. It is administered IV at 0.9% weight in volume. So we find that 0.9% is our normal saline, the normal saline we hear about in the hospital, and that is formed from our sodium chloride at a percentage of 0.9. So it is administered as normal saline, known as an isotonic solution. An isotonic solution is responsible for normalizing the osmotic pressure of blood. Okay, used for gargling in the upper respiratory tract infection. In case somebody has issues with the upper respiratory tract infection, by now we should know those different organs that we have in the upper respiratory tract. You find that we put it in the mouth and then the person googles. Like gargling is like you are rinsing the mouth, and after you spit it out, not split, you spit it out. Used for bath and swabbing. We see that our HCl can also be used for that. So let us see also medical uses of potassium chloride. Potassium chloride is used in cardiac arrhythmias and hypophosphatemia, and then usually administered as 10% oral aqueous solution. Identification test of alkali metal halides. So when we look at alkali metal halides, we still have to identify the cations and anions. The cations that we have sodium, we have potassium, those are cations. And then the anions, we shall have the chlorine, the bromine, and then the iodine. Or the other halogen compounds become anions. Anions are things with a minus sign. This one has a positive sign. This is a cation. So we have reagents we have to use for sodium ions. The reagent we majorly use here is zinc uranyl acetate in dilute acetic acid. So here is a statement you have to put it down. To a solution containing sodium ions. The solution containing sodium ions in solution, zinc uranyl acetate in the presence of dilute acetic acid is added and the mixture is shaken thoroughly. So we expect to observe. If we observe a yellow crystalline precipitate, then sodium ions present. If we have no observable change, we have sodium ions absent. And always give your answer in a two-way form, when it is present and when it is absent, so that you get all the marks. Okay, you have to convince the examiner and show them you know what you are doing and you know what you're writing about. That is why we have here when there is observation and when there is no observable change. Identification test for potassium ions. This is another cation that we shall have in those salts. We see that the reagent used here is tartaric acid in the presence of sodium acetate. So a solution containing potassium ions, tartaric acid in the presence of sodium acetate is added and the mixture shaken thoroughly. Observation, we see that a white precipitate is observed. We have potassium ions present. When we observe a white precipitate, it means potassium ions present. When we do not see any change, we shall conclude that potassium ions were absent or are absent. Sodium acetate solution is added in the reaction to prevent. This is the reason why we are adding sodium acetate. Is added in the solution to prevent dilution of the complex that is going to be formed, that is potassium hydrotartarate is a complex because we are getting it from tartaric acid. So we add it in order to prevent it from dissolving. Identification test for anions. We have the chloride, we have bromide, and we have the iodide. So here we have reagents that we use for our halogens, the anions. The reagent, if we remember very well, on a HCl, we also use silver nitrate. So silver nitrate works for all the three elements, or all the three ions of group 7 of the periodic table. So we have silver nitrate solution in the presence of nitric acid. So a solution containing anions, that is the chloride, the bromide, and iodide. Silver nitrate solution is in the presence of nitric acid is added and the mixture shaken thoroughly. So the first thing we want to observe is the chloride ions. When we see a white precipitate observed, chloride ions present. And this is the ionic equation for that specific reaction that will have taken place. When we want to observe bromide, we also add, we shall see a white or a slightly yellow precipitate observed. So bromide ions present. When we see that, and so since this slightly yellow precipitate confuses with white, we are still going to use ammonia solution and ammonium carbonate to distinguish the two, where we shall find that the silver chloride formed is going to be soluble in ammonia solution as well as ammonium carbonate, while our silver bromide formed is going to be soluble in ammonia but insoluble in ammonium carbonate, and that we shall be in position to give a conclusion. It is even written down here. So when we want to, let's first observe the iodide ions. We have a yellow precipitate observed, iodide ions present. Silver plus iodine, we have silver iodide. So silver bromide and silver chloride are sometimes difficult to distinguish by their color, hence another reagent used, ammonia solution and ammonia carbonate. Silver bromide dissolves only in concentrated ammonia solution but not in ammonia carbonate. So we see that this is what I was trying to tell you about. However, silver chloride dissolves in both dilute ammonia and ammonia solution and ammonium carbonate. Here also we have pharmaceutical assay of the salt, and that is majorly sodium chloride salt. So with the sodium chloride salt, we are going to have, since it is a salt, we are going to have what we call agent metric. So I'm going to talk about it in class, that assay. Okay, so that maybe we get the whole concept. Iodine. This is how we can interact with iodine. These are iodine crystals, how they can look like that grayish color. So sources of iodine. The chief source is this cheline nitrate, or excuse me, or calcium caliche. Sorry. That is a crude form of sodium nitrate from South America, which contains at least 0.0015% of the iodate. So extraction, we have mother liquors are obtained by liquefaction of the nitrate or treated with sulfide to precipitate free iron, which is washed and dried by passing. It can also be obtained by oxidation of the inorganic iodide present in brine wells and ashes of the seaweed. Purification, it is done by sublimation. And then we have physical properties. Iodine occurs as a heavy bluish black brittle robin prisms or plates, has an acrid taste with a distinct penetrative odor. It is slowly volatile at room temperature, and when heated is completely volatilized, giving off volatile colored vapors which condense as bluish black crystalline sublimates, as we saw those crystals in the other slide. Physical properties: contain a solution in alcohol, ether, or aqueous solution of iodides is a reddish brown, in chloroform or CS in violet colored, slightly soluble in water. Identification: when gently heated, it gives off violet colored vapor which condenses, forming a bluish black crystalline sublimate, and then gives a deep blue color with starch solution which disappears at boiling point.